So good morning, everybody. So today what we are going to start with is the concept of solid, and further we will also study how the solid modeling processes actually work. What is the algorithm behind the solid modeling processes or the softwares that you utilize. So the first thing that you need to basically understand over here is that how do you define a solid? That is the first thing that you need to understand. How do you define a solid? So solid has certain attributes which need to be fulfilled. So the first attribute that you need to fulfill for a solid is the boundedness. What do you mean by boundedness? Now boundedness over here means that any point which is representing the solid geometry or solid boundary, it should be lying within a finite space. First of all, it should be within a finite space, and the finite space is defined as a space within three-dimensional Euclidean space. A three-dimensional Euclidean space, that is, the space will be defined in terms of this axis. So this is x, this is y, and this is z. So all the points that are incorporated in order to define the solid has to lie first of all in a finite plane, and secondly, they should also lie in a known boundary, So that is the aspect of boundedness. Now the second most important aspect of a solid is that it should have a definitive boundary and have a solid interior. So if you ask what is a solid, the solid is generally defined as the boundary vectors union the interior points. So any point which is bounded has to have a definitive geometry. It is bound to have a definitive geometry. So when you talk of boundary, boundary is nothing but defining the extreme points, which are going to define the features of that individual object. And whatever points lie within that defined boundary, they are called as the interiors. So what is a solid? If you ask a very simple definition of solid, what is a solid? Solid is nothing but boundary vectors and the interior points. They joining together to form a solid. The third most important aspect of a solid is the boundary determinism. As I explained in the first point, the set of points has to lie in a finite space. So when they are lying in a finite space, a solid can be defined with respect to three axes, as I said, x, y, and z axis. The most important aspect of a solid is that if you plot a solid in two-dimensional Euclidean space, that is xy plane, yz plane, and zx plane. These are the three planes that you will generally work on, and this is the planes that you generally work in your software also. So if you are working on these planes, then what you have to understand is the curves or the surfaces which are excluding out of xy plane and yz plane or zx plane, they should not intersect each other such that the planes become redundant, Now what I mean by that, suppose this is one plane, this is suppose xy plane. Okay, now if I want to create another plane like this, which is basically the yz plane. Now yz plane should not cut the xy plane anywhere. It should rather meet the xy plane to create the boundary. Now if this plane shifts by some distance and starts to cut, then your solid is not a valid solid. Then your solid is not going to be a valid solid. So any number of planes that you can create, you need to understand this, that the planes should not intersect each other. That is, they should not be self-intersecting, they should be non-self-intersecting, and they should rather touch at the boundary positions rather than intersecting each other. So that is what we call as boundary determinism. Then there is another concept called homogeneous three-dimensionality. Now, what is homogeneous three-dimensionality? It is something which is very simple. Now, when you have a solid, now this is what we call as a dangling edge, and this is called as a dangling face. So if you have a solid, a very simple solid cube, now when you create an additional face or an additional edge, you have to keep in mind that this edge and this face should not undermine these two concepts. That is, the boundary and the interior and the boundary determinism should have to be satisfied even if you are creating an edge or an extra face. Okay, so if you are extruding something or if you are joining two different objects together, what you have to keep in mind is first of all, homogeneous three-dimensionality has to be taken care of, boundary determinism has to be taken care of, and the definition of boundary and the interiors has to be satisfied. The next point, which is very important over here to understand, is the rigidity. Now, what is rigidity over here? The rigidity basically means that this is point P1 and this is point P2. Now, if I shift P1 point by say 10 units along x-axis and 15 units along y-axis. Similarly, point P2 also. So the relative distance between point P1 and point P2, let us assume this as y dash. Let us assume this as y dash or x dash. So this x dash value should not change if I change the location of the points. So that is what we call as the rigidity. That means if I am repositioning a point or if I am reorienting a point, its relation with the neighboring points or the neighboring data should not change. That is what we call as rigidity. And then the last important aspect is closure. Now, what is closure over here means? The closure over here means all the above points, that is boundary, interior, homogeneous three-dimensionality, rigidity, boundary determinism should be satisfied. That means any object is called a solid object if it is a perfectly closed object. How do you check that closeness? I'll explain to you later on. But the closeness is basically defined as when two solids are being merged together by union command or addition command, any command that you want to do. When they are being merged together or when they are being cut from one another, the properties of the solid should not change. So that is what we call as closure. So when you talk of a polyhedral representation, the surface information is basically stored in form of faces, edges, and vertices. Now, what is this? Suppose you have a cube. Now, when you draw a cube, you know this is a cube because of its geometry. Okay, you know because of its geometry. But the software doesn't understand that this is a cube. The software is not going to understand this is a cube. For software, the data has to be in something that is rational. So the first rational object that our software understands is vertices. Now, what is vertex? Can anybody define what is vertex? Simple definition. I don't want a technical definition. A simple definition that you understand. What is a vertex?
So intersection of two edges.
Galat. It is a point in a three-dimensional Euclidean space. It's a simple point in a three-dimensional Euclidean space. Okay? Always remember that intersection is not a vertex. Intersection will never be a vertex. Okay? So what I am trying to say is that how many points are here which can be defined as a vertex? How many points are there which can be defined as a vertex?
8 points.
Very good. So let us name those points. 1, 2, this is 3, this is 4, this is 5, this is 6, This is 7 and this is 8. Okay. Now, if I want to define this cube, okay, how will I define this cube? Just see and try to understand how I'm defining it. The first thing I am defining is a face, okay, which is connected by edges, 1, 2, 2, 3, 3, 4, and 4, 1. Am I right?
Yes, sir.
Okay. And what are these edges consisting of? These are consisting of
Vertices.
vertices. So now can I define the complete cube? Now can I define the complete cube? Yes, I can define. I have 6 faces. Each face is consisting of edges, and each edges are being generated with the help of vertices. So what is the information that is being stored? The first information is vertex that you are defining in open space. Then you are connecting the edges, and at the end, joining the edges together, you are getting the faces. So what is the actual information you are storing? So the first information that you are storing is a vertex information. With the help of vertex, you are creating the edges, and with the help of edges, you are creating the faces. So this is the information that you are storing. Now, a very important aspect that you need to understand, what is the difference between a geometry and a topology? What is the difference between geometry and a topology? Okay. Sorry, this is not a correct figure. D. This is also D. This angle is phi. This is R. This is L1. Okay. Same thing happens over here. This is R. This is L1. Now, what you need to understand is, what do you mean by geometry and what do you mean by topology? Geometry basically means when two objects have similar physical dimensions and locations in 3-dimensional Euclidean space, then the object is said to have a similar geometry. Okay. What is topology? Topology is nothing but the connectivity between the two components, So if I start to compare this figure with this figure, what you understand is D is equivalent to D, L1 is equivalent to L1, R is equivalent to R. But what happens is the object is inclined at an angle phi. So when you find out the actual dimensions, L1 and D will not be similar. Okay? So they are not geometrically similar. Is it understood?
Yes, sir.
However, if I look at the connectivity, this is L1, this is L1, L1 is connected to D, L1 is connected to D, then this dimension is also L1, this dimension is also L1, and it is connected to a semicircle of radius R, which means the connections between the two components is similar. So they are topologically
Same.
Okay. Now, what you have to understand over here is that the topology is not actually looking into the dimensions. It is not actually looking into the dimensions. What it is looking is geometrical figures and their relative positions. Okay? So when you are talking about a topology, when you're talking about a topology, you have to understand that what is topology? It is the geometrical features and the relative positions. And what is geometry? What is geometry?
So study about dimension, surface area, volume.
Not volume, not surface area. Study about the dimensions of that object. ठीक है? Surface area and volume are the invariants of dimensions.
Yes, sir.
ठीक है? So when you talk of geometry, you are only talking about the physical dimensions or the physical unit of that object with respect to its measurement. Whereas topology is the relative position of that geometrical entities and their values. ठीक है? So when you talk of topology, topology is something which we actually refer to as rubber sheet geometry, because it can be converted into an equivalent figure by bending, twisting, stretching, and any other transformation, but not by cutting, tearing, and gluing. ठीक है? You cannot cut an object. आप ऑब्जेक्ट ऐसे नहीं कर सकते कि मैं ये ऑब्जेक्ट बनाया, इस ऑब्जेक्ट को काट दूं. इस तरह से हम टोपोलॉजी नहीं टेस्ट करते या चेक करते. टोपोलॉजी कैसे टेस्ट करते हैं? जैसे इसको हम, इस फिगर को हमने एक एंगल पे घुमा दिया था, ठीक है? तो अगर उसको हम ट्विस्टिंग भी कर रहे हैं पर उसके रिलेटिव पोजीशन सेम है, then still it can be checked for topology. ठीक है? If it is being stretched, like this L1 is not equal to this L1 dash, ठीक है? जैसे ये ऑब्जेक्ट बना दिया, ठीक है? Let us assume this is L2, this is L2, and this is D1, and this is R1. So this object geometrically is not similar to this. Understand? This is not similar to this object. This object. It is not. These two objects are not similar. But topologically, their relative values and their relative features are still same. So they are still topologically equivalent. So stretching also works over here. So when you look at topology and when you look at geometry, now what have you understood? That is what I want to know. What have you understood? Just give me a simple definition of geometry and topology that you people have understood.
So if we are comparing dimensions, we are talking about the geometry.
Yes.
And if we are comparing the relative positions, we are talking about topology.
I will even simplify that. If we are talking about the physical dimensions of an object and comparing the physical dimensions, then we are checking it in terms of geometry. And if we are looking into the correlations between the adjacent geometrical entities, and if those geometrical identities are similar, then they are called as topologically similar. A very good example is given over here. If you look very carefully, all these four figures are actually cubes. All these four figures A, B, C, and D are cubes. ठीक है? The only difference between A and B is that L is not equal to L dash, B is not equal to B dash, and C is not equal to C dash. ठीक है? But if I look at the relative positions, this is length, this is length, this is length, this is also length, this is length, this is also length. ठीक है? And this is also length. Hence, these two objects, that is A and B, are topologically similar. But are they geometrically same?
No, sir.
ठीक है? Why they are not geometrically same? Because the value of dimensions of height is not similar. ठीक है? Similarly, the value of width over here is not similar. The value is A, and here the value is B. So length, width, and height, the values are not similar, but topologically they are similar. Now look at this figure. What has happened? What has happened over here is you have an object which has been sheared, Okay? So when you look at this object, just look at this face, and look at this face. Are dimensionally equivalent? Are they dimensionally equivalent?
No, sir.
Are they proportionally equivalent? No, they are not proportionally equivalent also, because your length units are not similar. But are they topologically equivalent?
Yes, sir.
How?
So same, the adjacent position of the lines, edges are same, exactly same.
Yes, the adjacent position of the edges is similar. Or what you can say in a very simple terms is that this is also a four-sided polygon. The face is also, this face 1 is a four-sided polygon similar to face 1 of the image A. Okay, na? So when some object is topologically equivalent, then the property of topological equivalence is called as homeomorphism. Then this property is called as homeomorphism. Okay? So a very classic, this is a very classic example of homeomorphism that you are seeing. A simple cube in different forms. Now what is this figure? Can anybody tell me what is this figure?
So it's like a top view of a pyramid.
It's a top view of a pyramid, but it is not a normal pyramid. It's a square pyramid or
Yes.
a rectangular pyramid. Okay? If I give you the side image, the side image will be something like this.
Yes.
Okay? So if I stretch it, it will be something like this, then this, then this. So this is what you are seeing. So the interesting part is, if you look at this face, simply look at this face. Just look at this face. And look at this face, face 1. Is it same with respect to figure A, figure B, and figure C? Is it same?
Topologically, it is same, but not
Yes.
geometrically.
Geometrically, it is completely different. है ना? But topologically, it is same. Why? Because in figure D also, the face 1 is a four-sided polygon. Whereas in figure A also, it is a four-sided polygon. But the difference of dimensions is also clearly evident. So if I start to compare A with D, what would be my conclusion?
So they both are topologically same, but geometrically different.
Yes. In very simple words, what we say is A and D are homeomorphic. A and D are homeomorphic. So homeomorphic basically means two objects who have same topology but different geometries. Now, आप में से कितने लोगों ने वड़ा खाया है? सबने खाया है?
Yes, sir.
Yes.
वड़े का शेप क्या होता है?
Like a donut.
Donut भी एक shape है. Donut is also a shape. ठीक है? What is that shape? It has got a circular ring with a hole in the center. Right? आप सबने बचपन में साइकिल चलाई है? अभी भी चलाते होंगे शायद?
Yes.
Yes,
साइकिल
sir.
का ट्यूब देखा है?
Yes.
Yes, sir.
क्या होता है?
Donut.
Large donut.
It is not a donut, but it's a circular tube which has got a space at the center or a hollow through hole at the center. Am I right?
Yes.
ठीक? So what is that? A donut, a cycle tube. What is that?
So topologically same and geometrically different.
So please use this word.
Homeomorphic.
They are homeomorphic.
Homeomorphic.
ठीक है? अच्छा, अब सपोज करिए, जस्ट अज्यूम करिए आपके पास एक स्फीयर है, नॉर्मल एक स्फीयर है, छोटा सा, ठीक है, और आपने क्या करा, स्फीयर के सेंटर को पकड़ के उस पे एक 5 mm का थ्रू होल मार दिया. ये फिगर, ठीक, ये आपका साइकिल ट्यूब है. तो आप किसी भी ऑब्जेक्ट के साथ होम्योमॉर्फिक बना सकते हैं. Geometry is not important when you are trying to put up a homeomorphic image. How do you change this object, that is figure F into figure G. How can you change this figure F into figure G? Any ideas?
सर अगर स्क्वीज कर दें उसको टॉप पर से बॉटम पे से.
So basically what you are saying is either by bending, stretching or twisting. ठीक है ना?
Yes.
You can create this object that is of figure G out of figure F.
Yes sir.
So that is the whole process of transformation that you will learn in the next lecture. So homeomorphism is a property where you have an object with you and you can take that object and create an object with a similar properties but with different dimensions. ठीक है? So homeomorphism can be shifted also. ठीक है? Homeomorphism can be shifted also. Okay. Now let us summarize what we have done up till now. Let us summarize. What is a solid? Solid is an object which is going to be bounded and should have connections. Solid is an object which has to be bounded and which needs a connections, and it is bounded where it is going to be defined within a finite space. Please remember that. ठीक है? Solid object has to be defined in a finite space. जैसे आप एक कुछ ऑब्जेक्ट बनाते हैं तो जब आप सबसे पहला काम क्या करते हैं, आप जब अपना स्क्रीन खोलते हैं और आप एक प्लेन डिसाइड करते हैं. ठीक है? सपोज यू डिसाइडेड दिस प्लेन टू वर्क ऑन. दिस इज द प्लेन दैट यू वांट टू वर्क ऑन. सो व्हाट इज द मीनिंग ऑफ सिलेक्शन ऑफ दिस प्लेन? Selection of the plane basically means that what you have actually decided is that this is the domain in which I will work and this is the boundary that I am defining for the object. And within that boundary, when you plot the two-dimensional image, when you plot this two-dimensional image, what is this? What are these four lines representing actually? What are these four lines actually representing? Suppose this is the plane on which you have plotted this. What are, pardon?
Boundary.
Exactly. So that is what is happening over here. You are defining the object in a finite space. You are defining that object in a finite space. Now, when you have connected the boundaries together, what is this part? जहां पे मैंने scratching कर रहा हूं. What is this part?
So control volume.
No, that is the interior of to the solid.
Yes sir, interior. Yes.
ठीक है? So now again I'll go back to the simple definition. What is a solid? The boundary union interior. ठीक है? So what is a solid? The boundary points and all the interior points joining together will give you a solid. Now, what are the four most important aspects of a solid? It should have a closed boundary, जो कि आपने अभी देखा. It should be perfectly orientable. It should be connected, and most important thing, it should have a non-self-intersecting plane. It should have a non-self-intersecting plane. ठीक है? A closed surface basically is one having no boundary for this. जैसे स्फीयर है. अब स्फीयर में कोई बाउंड्री नहीं हो डिफाइन करते हम. जैसे हमने क्या किया, जैसे एक स्फीयर बनाया. ठीक है? दिस इज हाउ वी डिफाइन अ स्फीयर इन 3-dimensional space, not like this, sorry, like this. So this is a sphere. So इस स्फीयर की कोई बाउंड्री नहीं होती है, पर हाँ इसके कंट्रोल कर्व्स होते हैं. ठीक है? तो स्फीयर को डिफाइन करते समय हमको ये याद रखना होता है कि यहाँ पर एक बाउंड्री कोई नहीं है, पर कंट्रोल कर्व्स बहुत सारे हैं. सिमिलर वे में अगर मैं इस टोरस को ध्यान से देखूं, ये टोरस है, इस टोरस को ध्यान से देखूं तो मुझे क्या दिखाई देता है कि यहाँ पर कंट्रोल कर्व्स है. ठीक है? ये बाउंड्री नहीं है, ये कंट्रोल कर्व्स है. ये बाउंड्री नहीं है, ये कंट्रोल कर्व्स है. तो कई ऐसे ऑब्जेक्ट्स हैं जैसे स्फीयर और टोरस जिसमें एक क्लोज सरफेस तो हम जनरेट करते हैं, बट उसमें कोई बाउंड्री नहीं होती है. जो कंट्रोल कर्व होता है वही बाउंड्री कर्व का काम करता है. ठीक है? होमियोमॉर्फिज्म जो है, होमियोमॉर्फिज्म आप किसी भी क्लोज सरफेसेस के लिए क्रिएट कर सकते हैं. होमियोमॉर्फिज्म आप किसी भी क्लोज सरफेस के लिए क्रिएट कर सकते हैं. जैसे बहुत सिंपल सा एग्जांपल देता हूं. आपके पास घर में जो प्लेट है, आपके घर में जो प्लेट है, ठीक है, जिसमें आप खाना खाते हैं, वो प्लेट किस ऑब्जेक्ट के जैसे रिफ्लेक्ट करती है?
Disk.
A frisbee disc, something like a frisbee disc also.
Yes, sir.
ठीक है, so always keep in mind that the objects can be homeomorphed or correlated to any object. The idea of homeomorphism is so that you understand that one object using transformations can be converted into another object with different geometrical features but having the same identifiers. अच्छा, अब आते हैं बाउंड्री कर्व्स पे। बाउंड्री कर्व क्यों इंपॉर्टेंट है? बाउंड्री कर्व्स इसलिए इंपॉर्टेंट है क्योंकि बाउंड्री कर्व्स डिफाइन करते हैं हमारी एक सॉलिड की आइडेंटिफिकेशन के लिए। मतलब मेरा सॉलिड अगर क्लोज नहीं होगा या उसमें बाउंड्री कर्व्स डिफाइंड नहीं होंगे तो मैं उस सॉलिड को वैलिड सॉलिड नहीं कह सकता। ठीक है, तो अगर मैं एक सर्किल बनाता हूं, सिंपल सा एक सर्किल, इस सर्किल के कितने बाउंड्री कर्व्स हैं? इस सर्किल में कितने बाउंड्री कर्व्स हैं? बताइए।
सर हम काउंट कर सकते हैं?
हाँ 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 हाँ, सिंगल बाउंड्री कर्व है ना। एक सर्किल में कितने बाउंड्री कर्व होते हैं? सिंगल।
ओके, हम क्लोज कर्व की कंसीडर कर सकते हैं।
हाँ, बाउंड्री कर्व क्या है? जिसने क्लोज कर दिया ना अपने आप को।
यस यस।
अच्छा ठीक है, ये एक ओपन एंडेड सिलेंडर है, ओपन एंडेड है, इसमें कितने बाउंड्री कर्व्स है? एक ये बाउंड्री कर्व और एक नीचे बाउंड्री कर्व, तो इसमें कितने बाउंड्री कर्व्स है?
टू बाउंड्री।
अच्छा, अब मैं एक शेप बना रहा हूं, अब बताइएगा। ये एक ओपन एंडेड नॉन क्लोज सिलेंडर है, इसमें कितने बाउंड्री कर्व्स है? ये एक ओपन एंडेड नॉन क्लोज सिलेंडर है, इसमें कितने बाउंड्री कर्व्स है?
3।
गलत।
सर वन ही दिख रहा है, मतलब अगर वो क्लोज अगर हो तो एक ही तो दिख रहा है।
नहीं,
सर ओपन एंडेड में डिफाइन कैसे करेंगे?
एक, दो, तीन, चार, इसको खोल दो, क्या बन जाएगा ये? ठीक है,
ओके हाँ, उसको हमने रोल कर दिया। यस सर।
तो यहां आपकी इमेजिनेशन की बहुत सख्त जरूरत है। ठीक है,
Yes.
यहाँ इसीलिए कैड मॉडलिंग करते समय व्हाई वी से दैट कैड मॉडल नीड्स इमेजिनेशन इज फॉर द सेम रीजन दैट यू नीड टू अंडरस्टैंड that the boundary curves have play a very significant role in putting the solid as a valid solid, because generally what happens is if you have to make a cube, what you generally do is you create a square, okay, and then you extrude this square in z axis. Simple, you give the extrusion command and you give the data and it is extruded. So a cube is going to be solid only when the base is going to remain a solid. Base is converts into solid when it is covered by boundary curves which are closed, bounded and connected. The curve which is closed, bounded and connected. ठीक है, so the closeness of the curve and the connection of the curve, that is why it is so important over here. Now once the solid has been developed, you need to understand what are the invariants of surfaces, because solid is not doing anything but what is a solid. If you ask me what is a solid, what I'd say is solid is nothing but surfaces covering the face of the object. ठीक है. व्हाट इज सॉलिड? सॉलिड इज नथिंग. सपोज अगर इसकी बात करें, एक सिंपल सा क्यूब ले, सिंपल सा क्यूब, बिकॉज क्यूब इज द एग्जांपल व्हिच आई फाइंड सूटेड फॉर एवरीथिंग. अगर हम इस क्यूब को लें और इस क्यूब को डिफाइन करने के लिए कहें, तो जैसे मैंने पहले आपसे कहा था, हाउ मेनी फेसेस इट हैज गॉट? इट हैज गॉट 6 फेसेस. ठीक है. व्हाट आर दोस फेसेस? इफ यू डिफाइन व्हाट आर दोस फेसेस, they are surfaces which are intersecting each other at a certain edge. ठीक है. Which are intersecting each other at certain edges. And what are those edges going to define you? The edges are defining the boundary components. So when you want to calculate what are the number of boundary components for an object that you have got, that can be done with the help of an integer which is c. Now here what you can understand is that for a torus, as I explained, there is no boundary curve. For a disk or a hemisphere or a circle, there is one boundary curve. For an open-ended cylinder, the boundary curves are 2. So the value of c ranges between 0, 1, 2, 3 and 4, and this is the generally the maximum value that you will get. Okay. The second thing is orientability. Now orientability is given by the value of epsilon, and it only has got two values. Either the epsilon will be 1 or either the epsilon will be 0. Okay. So any surface that is orientable, that is given the value of epsilon 1, and any surface which is non-orientable, it is given as 0. Now what is an orientable surface? An orientable surface has two distinguishable sides which can be labeled as inside and outside. ठीक है. जैसे ये हमारा क्यूब था. ठीक है. अगर हम इस क्यूब को, अगर हम इसी क्यूब को एक फेस ले ले, कि कोई एक फेस ले ले, कोई सा भी है, सपोज हम फेस 1 ले रहे हैं जो फ्रंट फेस है मेरा, मैं इस तरह से देख रहा हूं, फ्रंट फेस है. अगर मैं इसको बाहर से देखता हूं तो मैं बता सकता हूं कि ये आउटसाइड है, और अगर मैं इस क्यूब के अंदर जाके इसको इस डायरेक्शन में देखता हूं तो मैं बता सकता हूं कि वो इनसाइड है. ठीक है. सो पोजीशनिंग ऑफ अ व्यूअर decides or governs the value of orientability, the positioning of the viewer. So if you can identify the two distinguishable sides of the same face, then you can say that epsilon is 1, that is the surface is orientable, otherwise the surface is non-orientable. Okay. Now what is genus? Genus is it is again an integer which will be given by the value of g. ठीक है. Genus basically represents the voids that are there in the object. जैसे again my standard example of cube, and let us assume that there is a hole throughout the surface. So this hole is called as genus. ठीक है. This hole is going to be called as genus. So if there is one hole which is throughout, then the genus is equal to 1, or that is equal to g. However, if this hole is actually not going throughout the surface, if this hole is not going throughout the surface, in that case the value of genus is assumed to be 0. The value of genus is assumed to be 0. So the idea is that the void should be complete on the orientable surface. The void should be complete on the orientable surface. So that is why a sphere has 0, whereas torus has 1. So if you go back and see the image of torus, so this is the through hole that you can observe. Okay? Similarly, this is the through hole that you can observe. So here the value of g is going to be 1. But if you take a simple disk, the value of g is going to be 0. Okay? Acha. I have a simple question to ask you right now before I finish. आपने चाय पी है कप में सबने?
Yes, sir.
Yes, sir.
चाय के कप में जीनस की वैल्यू क्या होगी?
0.
0, sir.
मैं फिगर बना रहा हूँ, फिगर ध्यान से देख लो. चाय के कप में जीनस की वैल्यू क्या होगी?
1 होगी सर।
क्यों?
सर यहाँ पे सर टॉरस भी है साइड में, तो उस केस में फिर 1।
चाय का कप में फिर पकड़ोगे कैसे? समझ में आया?
यस सर।
जो हमारा ये वाला पोर्शन होता है जिसपे हम पकड़ के कप को उठाते हैं, ये पोर्शन, दिस बिकम्स अ
जीनस। यस।
ठीक है. सो यू हैव टू लुक वेरी केयरफुली एट द ऑब्जेक्ट कि does that object have a through hole or is it a hole which is not going through the system? So if you look at this hole, this is not going through. ठीक है, ये नीचे से covered है. But if you look at the handle part, it's a through hole. ठीक है. So genus over here will be equal to 1. Then there is a factor called Euler characteristic. And this value of Euler characteristic is given by the formula zeta, where zeta is equal to vertices minus edges plus faces. So this is the formula of zeta, and the value of zeta depends upon these three basic factors. So if you have a cube, can you calculate the value of zeta? How many vertices are there?
8,
8 vertices.
How many edges?
6. Sorry, 12. Sorry. It's
How
12.
many faces?
6.
6.
So zeta is equal to
-4 plus 4 2.
ठीक है. So zeta equal to 2. This is how you calculate the values. ठीक है. अच्छा, what will be the value of zeta for a sphere?
No vertex, no edges, no faces. 0.
1.
Face control.
फेस 1 होगा ना सर?
हाँ, control.
जब भी आप किस भी एक्सिस से देखोगे उसका एक फेस आपको दिखाई देगा ना.
Yes, sir, sure.
So face equal to 1. So zeta will be equal to
1.
Now comes a factor called connectivity number of the surface. Now what is connectivity number of a surface? Connectivity number basically tells you that in how many steps or how many number of cuts I can separate that object into two distinguishable objects. I can cut that object into two distinguishable objects. ठीक है. जैसे एक स्फीयर लीजिए. ठीक है, स्फीयर के नाम पे अपन एक अज्यूम कर लेते हैं एक सेब है. अगर मैं सेब को बीच में से एक कट मार देता हूं तो वो दो अलग अलग ऑब्जेक्ट्स में चेंज हो जाता है. दो सेमी स्फीयर आ जाते हैं ना.
Yes, sir.
ठीक है. सो दैट मींस इन अ सिंगल कट आई कैन कट द स्फीयर इनटू टू डिफरेंट ऑब्जेक्ट्स. सो दैट इज कॉल्ड as a simply connected ऑब्जेक्ट. ठीक है. अगर एक ही कट में हम किसी को अलग कर सकते हैं, तो दैट इज कॉल्ड एज अ सिंपली कनेक्टेड ऑब्जेक्ट. ठीक है. चलिए अब एक एग्जांपल देता हूं और वापस आते हैं टॉरस पे. इस टॉरस को दो अलग अलग ऑब्जेक्ट्स में क्रिएट करने के लिए मुझे कितने कट्स लगाने पड़ेंगे?
तो हम डायमेट्रिकली अगर एक ही कट लगाएं तो
नहीं, तब भी नहीं होगा. सबसे पहले आपको एक कट यहां लगाना पड़ेगा ताकि ये लंबा एक सिलेंडर बन जाए. ठीक है. आया समझ में? सबसे पहले इसको डायमेट्रिक एक्सिस पे कट लगाएंगे ताकि ये एक इस तरह का ऑब्जेक्ट बन जाए. ठीक है. उसके बाद अलोंग द लेंथ एक कट लगाएंगे जिसमें ये एक सरफेस बन जाएगा, और उसके बाद इसके एक्सिस पे एक कट लगाएंगे जिससे कि ये दो डिफरेंट ऑब्जेक्ट्स बन जाएंगे. सो कितने कट लगे? 1 2 3. ठीक है. सो in order to cut a torus, the value is coming out to be 3. That means it is triply connected. ठीक है. So I am stopping my lecture today over here. ठीक है. And we will continue tomorrow.